Good morning, dear colleagues and conference participants. So my talk is devoted to implementation of revival of silence echo memory protocol in erbium YSO crystal. So it's not a thulium aluminum garnet crystal, it's erbium YSO. And a little words about what is an optical quantum memory. It's a device that allows you to save an arbitrary state of qubits for a given time. So you can imagine it like a black box. So at the input you have a qubit, yes, and then you should absorb it. You must the quantum memory cell must absorb it, and then on demand after storage, you should give it back, and the fidelity of the states should be the same. So there are several criteria for such quantum memory, like efficiency, storage time, central wavelength capacity, and so on. Quantum memory can be applied in different areas of modern quantum technologies, like quantum communications, quantum metrology, single photon source and detectors, and also in quantum computing. On the last 2 decades, several quantum memory protocols were proposed. So the protocol is how to absorb and then re-emit the input single photon field. So our group work with photon echo approach, and currently with revival of silence echo memory protocol. It is known that usual primary echo or 2-pulse photon echo sequence can be used for as quantum memory protocol, because after applying the rephasing pulse, pi pulse, all atoms are staying at the excited state. So you can't detect your single photon, because there will be many photons from the excited state from spontaneous emission. But you can apply the second pi pulse and bring the system back to the ground state. And in this case, if your rephasing pulses have a good quality, you can then observe just input pulse. But in this scheme, it's very important to suppress the primary echo signal. And it can be done with geometry of propagation of input pulse and rephasing pulses. So there are such schemes. For example, this is called a forward scheme. So as you see, the input pulse and Rose echo signal are propagating in one direction. But in this case, the maximum efficiency is limited by 54%, caused by a reabsorption of echo signal in the crystal. But it can be, we can obtain efficiency close to 100%, for example, in scheme 3, yes? And this scheme is called backward scheme. So the echo signal is antipropagate to the input signal, to the input pulse. And in the case of 3, for example, you should have a very large optical dense. And this is not so good to have a good absorption of your input pulse. And for example, and the next step is you can put your crystal to optical cavity. And here you can use the crystal with low concentration, so with lower optical dense, and you can obtain efficiency about 100% theoretically. Yes, and such schemes, as you see, was implemented before in different works and in different type of crystals, also in erbium YSO. And why we choose the erbium YSO crystal? First of all, it has an optical transition close to 1.5 micrometers, which is very interesting for application in telecommunications. And it has, the second one has a recordly narrow homogeneous line, so the coherence time is very large for optical transition. So as you see, at the specific cases, the homogeneous line width can be as low as 70 hertz. So the coherence time will be about 4 milliseconds. And it is important for us because in photon echo memory, the efficiency of the input pulse retrieval is drops with exponential for storage time, with the storage time. Next one, that erbium is a first of all, Kramer's ion, and it has a 167th isotope with 7½ spin, nuclear spin. And it is known that the coherence time between this hyperfine transition can be very, very large. And so, for example, the Australian groups demonstrates that in specific cases, the coherence time between hyperfine transition can be 1 second. And it's very good and very interesting for further applications. Next, different photonic crystal cavities was implemented and fabricated in this crystal. And this is very interesting because you can use it as integrated optics, like waveguides and so on. And also you increase the interaction between light and atoms. And for example, the Jeff Thompson group showed that they detected just one that signal from one erbium ion and used it like a single photon source. Moreover, another group also in such cavity in this crystal, they initialize the spin state, the initial spin state of 4 ions coupled to one cavity. And you see, it's very interesting for further applications. So we can initialize in different states of 4 ions. So this is interesting for implementation of revival of silence memory protocol in this erbium YSO crystal. As was said before, it is really important to implement pi pulses, refacing pulses with very good quality, because the disadvantage of this protocol, of this scheme, is a spontaneous emission. So if you will not have a pi pulses, really pi pulses, then you will have a remain at the atoms will remain on the excited state, and this spontaneous emission will cause this quantum noise. So instead of usual Gaussian pulses with single frequency, with complex hyperbolic second pulses, where the amplitude and frequency are modulated with these equations. And it is the second advantage of such pulses that they are more robust in optically dense medium. As you see on the left side, it is absorption spectrum, and absorption quite high, so about 5. So this is a scheme of experimental step. We used collinear geometry, so the forward scheme. So the maximum achievable efficiency in our case is 54%. And moreover, we use a special Gauss called Gauss to top hat lens to transform the Gaussian beam profile to such very stable, like square profile to have a minimum variation of intensity. Here I demonstrate results with 4 bright pulses. So black one is the input pulse, and then by blue and yellow, there are shown the rose echo pulses. So if we, in the case of using identical rephasing pulses, we achieve the efficiency of 40%. If the intensity of first pulse is bigger than the second one, the efficiency can be 58%. And it is interesting that the maximum achievable efficiency in our case with alpha L and coherence time is 47%. So next we investigated this by variation of intensity of these pi pulses, of rephasing pulses, and this is the different areas of where the efficiency of input pulse retrieval is bigger than 45%. So, and for diagonal elements, we see that we are really close to 40%, but the maximum is 47%. So, and where is, it's interesting why we didn't obtain 47%. And here, to analyze this graphic, we use pulse area theorem approach. So, but here is for free space. So Sergei Andreevich Moiseev talked before about the waveguide, that area theorem for waveguide. Here we use it just for free space system. there are equations for first, second, third pulses. Then we have solutions for these equations. And using these solutions, we can write the same, likely the same equation for echo pulse. Yes, and the solution will be in this form. And here, you see, so our experiment, as I showed before, the maximum efficiency 47%. The blue solid line is the theory, so this is t quadrat, t square. Yes, but qualitatively, our experimental data is very well fit with theory if we apply this theory by 0.8. And the possible reasons could be in the implementation of these rephasing pulses. For example, so we use here we use intensity, and we implemented these pulses with acousto-optical modulator, and we sent to acousto-optical modulator the amplitude modulation in such form, but caused by the nonlinear transponse function of acousto-optical modulator, it was not direct this second in square. For the low intensities, it was about seconds in the power of 3, and for large intensities, it was seconds in the power of 1.7, for example. Yes, and we checked this the quality of rephasing pulses with different methods by spectral hole building. So the black line is just the absorption. So alpha L is equal to 2.4. Just this probe pulse in 3 megahertz bandwidth. Yes, then we applying just first pi pulse and see this inversion shown by blue line from 2.4 up to -2. Not so good, but okay. Then we use both pulses, and we see that there is no inversion. Here in the spectral region of, in the working spectral regions of these pulses, we have quite glad line with alpha L about 1.5. From this, we can obtain, we derive that the efficiency of rephasing pulses is about 80% in our case. And by dotted lines, there are just Bloch equations. We analyze this by Bloch equations, and you see also big spectral regions with quite high level of atoms that state in excited state, and this will cause maybe very good, very large quantum noise. And further, we implemented this protocol on a few photon 11 in erbium wire crystal. So we use single nanowire superconducting detector, single photon detector. Yes, and in this case, the input pulse contained about 300 photons, 340, and the Rose echo signal contained about 150 photons for the signal to noise ratio about 4. So the noise floor in the echo temporal mode is about 40, which is not so good. We want to obtain this noise floor about 0.1 and smaller. So, perspective, what can we do? First of all, using erbium wire crystal with low concentration and putting it into the cavity. It can be as such a free space cavity like Fabry-Perot, or photonic crystal cavity, which is more attractive. Yes. With this, we can lower the concentration of erbium ions and increasing the coupling constant between light and atoms. Then, preparing artificial absorption line. For example, the spontaneous emission from these regions, spectral regions, are responsible with a factor of 4, maybe. Yeah, with factor of 4. Yes, and we can prepare so artificial line to remove the atoms from these states. So we will have just a square here, and it can be done in this crystal. And in 2018, it was shown that the T1 times the spectral whole lifetime at hyperfan transition can be as large as 60 seconds, so it's 1 minute. And it's really interesting to use such technique to prepare the artificial line. Yes, and then here in this work we used a magnetic field. We apply a magnetic field, about 2 kilogauss, yes, and obtain a phase memory time about 280 microseconds. And then increasing the magnetic field up to 4 Tesla, for example, we can obtain bigger phase memory time up to 500 microseconds and larger. So, and the main problem is the p-pulses modification and working on the implementation of these pi pulses, because no one in ensemble system achieved really, also in our community, a good quality of these pi pulses. So everyone have a quality of pi pulses, efficiency of these phasing pulses about 50%. Thank you for your attention.
Thank you, Mansur. Well, we have some time for questions, please. Well, Mansur, just to recap, you mentioned a factor of 0.8 to match the theory to experiment. Yeah. So what's the reason, minor reason for this factor correction?
So, as I said, we suppose that the main reason is the implementation of this, the nonlinear transparency functions of acoustic-optical modulator. So
not right implementation of this shape of the pulse.
Yeah.
Phase modulation
so
of this
the
pulse.
shape is different from this one.
I see.
So, for example, the equations were solved for such pulses.
Yeah, but did you try to simulate this with another pulse shape?
Not yet.
Yeah, okay. Other questions?
May I ask a question?
Yes, please, Maria Nikolaevna.
Do you hear me?
Yes.
Mansur, why do you plan to use crystals with lower erbium concentration? What is the advantage of using lower concentrations?
Thank you for your question, Maria Nikolaevna. So the main point is that our pi pulses, rephasing pulses, will better propagate in such medium with lower optical density. So this high alpha L really absorb rephasing pulses and disturb them. So we can't reach really high efficiency of rephasing pulses. Mm-hmm. It's one from one side, and second one, low concentration is better for us, as we see from this work also.
Thank you.
Okay. And yes, and the third one is quantum noise. So if we, for example, here we used a sample with 50 ppm concentration of erbium ions. So for example, lowering the concentration will give fewer atoms, and so we can suppress this quantum noise by a factor of 10.
Okay, thank you.
Well, thank you.